Hi everyone. In the previous lectures, we introduced the idea of a differential amplifier. And we said for a differential amplifier, we define three different gains. The first gain is the differential gain, which is measured by feeding a differential input and measuring the differential output in response to the differential input. So the differential gain is the actual gain we designed the differential amplifier for. So it's nothing but it's defined as the ratio of the differential output voltage to the differential input voltage. The next gain is the common mode gain, wherein we apply the same inputs at the two input terminals of a differential amplifier and then see how both the terminals respond to that, how the output terminal respond in a common mode way. So we took the average of the output voltage and the average of the input voltage, took the ratio of that, and we defined that as the common mode gain. The third and the most important gain is a CMDM, which is the differential mode gain for a common mode input. So a CMDM, we said, for an ideal differential amplifier should be equal to 0, and it's also a measure of how symmetric the circuit is. We took an example of this circuit which is shown here. So this is actually a constant voltage biasing, because if you see at DC, the gate voltage is at VCM, source voltage is at VS, so the VGS is always fixed. So this is a constant voltage biased differential amplifier. And we applied differential inputs, common mode inputs, and tried to find out all the three different gains. So for this amplifier, we concluded that the common mode gain and the differential gain are exactly equal, and we said is equal to GM times R. And we said that made intuitive sense, because if you see the way in which we are going to construct a differential amplifier is that we take two identical the single-ended amplifiers. Then using this combination of two identical single-ended amplifiers, we can then construct a differential amplifiers by feeding inputs differentially and taking the outputs differentially. So we said by that, intuitively it made sense that both the common mode and the differential gain for this amplifier had to be same. And we also said ACMDM, we spoke about ACMDM, and we said that for a purely differential circuit it should be 0. But in an actual circuit, no circuit is purely differential, so there will be some asymmetry between the two amplifiers of a differential, two arms of a differential amplifier. And because of that, this ACMDM will not be exactly equal to 0. So therefore, this ACMDM is a measure of how symmetric a differential amplifier is. And towards the end of the previous lecture, I said that we will take an example and show that the common mode and differential mode gains need not be same. So to that end, I'll consider the circuit that is shown here. So this is a current biased differential amplifier. In fact, so this is it's what we call as a differential pair. So we have a pair of transistor forming a differential amplifier. So shown here is a MOS based differential pair. So here this is a current biased because your current is fixed. So if the circuit is purely symmetric and I'm going to apply same DC voltages at both the gates, then you have the DC current splitting equally. So you have a current I by 2 and I by 2 between the two transistors, and that helps in biasing both the transistors. Now this configuration where the source of both these transistors are tied together, it's what is referred to as the source coupled differential pair. In fact, the idea of using differential amplifiers predates the inventions of MOSFETs and BJTs. So it was used at the times of vacuum tube amplifiers in 1930s. At that time, it was called the cathode coupled amplifiers. So just to quickly review, so you have a vacuum tube amplifiers, then we had BJTs and MOSFETs. So in case of a MOSFET, we have gate, drain and source. In case of a BJT, it's base. The equivalent for drain will be your collector and its emitter for source. And in vacuum tube amplifiers, it is grid, and for drain it is anode, and for emitter it is it's cathode. So therefore, it was called the cathode coupled differential pair. So this amplifier structure where we had two MOS amplifiers with their source tied together and used as an amplifier was called, in those days using vacuum tubes, it was called the common or the cathode coupled differential pair. And then later in BJTs it was called the emitter coupled differential pair. And now in MOSFETs it was later called the source coupled differential pairs. Now we are going to analyze all the three important parameters, which is ADM, the differential mode gain, ACM, the common mode gain, and ACM-DM. To first find the differential mode gain, I am applying a differential input Vi by 2 and minus Vi by 2 on both the sides, and then we will see what is the differential output voltage here. So first I will short circuit all the AC sources and open circuit the current sources. So I am going to open circuit the current source, and DC sources are all short circuited. So we have the AC equivalent. The AC equivalent reduces to something like this. Now we are supposed to find the voltage gain of this amplifier. Now here the source node voltage, unlike if you remember the previous example, which is a voltage biased differential pair, the source voltage was at ground, AC ground. So we directly saw that the entire VGS was equal to the input voltage itself. Vs by 2 was equal to VGS itself. But now since the source node voltage is floating, we don't know what this voltage is, and we have to find that out. Now I'll do a brute force way of finding it, and then we'll also find it intuitively. So the brute force way is that we can quickly see that the small signal current I1 flowing in this MOSFET plus the small signal current I2 flowing in this MOSFET, the sum of the two currents should be equal to 0. So this node is open, so the current is 0. So I1 plus I2 should be equal to 0. I1 is nothing but GM VGS1. So I will call this as MOSFET 1, MOSFET 2. So this is VGS1, and VGS1 happens to be Vs by 2 minus, let this node voltage be Vx, and VGS2 happens to be minus of Vs by 2 minus Vx. So I'll take the minus common out. So this is your VGS2. The sum of the two currents, GM into VGS1 plus VGS2, is equal to 0, or I can write VGS1 plus VGS2 equals 0. So add the two voltages, you get Vs by 2 and Vs by 2 cancelled out, you get Vx equals 0. Okay, so this is I actually get GM into VGS1 plus VGS2 equals 0, but since you have biased this amplifier with a certain finite current, so GM cannot be 0, so then this term has to be 0. So from that we see that Vx is equal to 0. But we can also intuitively see that it's a differential amplifier where both these amplifiers are identical and you are applying a differential input to both these amplifiers. So this node, if you recall from the previous lectures, we said will automatically come to differential ground. This node will come to AC ground. If you apply differential inputs, it's going to come to AC ground. How do we analyze that? We can apply the principle of superposition. So first I'll assume this is 0, and if I'm applying an input here, let's assume R0 is infinity for simplicity of analysis. If I assume R0 is infinity, the looking in resistance here is 1 by GM. So the second transistor will act like a load for the first transistor, and you have a common drain configuration with a source resistance of 1 by GM, so the gain is half. So you get Vs by 4 because of this input. In the same way, we can also calculate what will be the contribution because of the negative input. So I'm going to apply minus Vs by 2 now, and this will be 0. You will get minus Vs by 4. Because it's a symmetric circuit, I can directly say that it's minus Vs by 4, so it will be 0. So only if you apply differential inputs, so plus Vs here and minus Vs by 2, plus Vs by 2 here and minus Vs by 2 here, you will get this node will come to AC ground. So that's why to distinguish this from a conventional AC ground, if you see when we analyzed the voltage biased circuit, this node was at AC ground because we connected a DC voltage source here. So that node was at AC ground. Whether the input is differential or not, it doesn't matter, it was at AC ground. But here, this node goes to AC ground only because the inputs are differential. If the inputs are not differential, this node will not go to AC ground. Now once we know that, now we can easily calculate, now we know the source potential. So the source potential is 0. So we can easily calculate the voltage gain. So the circuit reduces to two common source amplifiers, and with inputs plus minus Vs by 2 on either sides. So the gain VO minus will simply be minus of GMR into Vs by 2. So the minus comes because of common source, it's a common source amplifier. And VO plus will be plus GMR into Vs by 2. So that's this node here. So the differential output voltage will be GMR into Vs. So the gain is going to be GMR. Just to quickly refresh your memory, this is the same gain we got for a voltage biased amplifier as well. We got the same differential gain for that circuit as well, and that's not surprising so far. The next step is to find the common mode gain. Now I'm applying a common mode input at both the inputs of the MOS amplifier, and then we'll see what will be the outputs on either of these terminals. Again, we'll follow the same procedure. I'll assume the DC voltage sources are at AC ground and open circuit the current sources. We reduce to a circuit like this here. Now to find the voltage gain of this circuit here, to find the voltage gain or the common mode voltage gain, I need to first find out what is the VGS, the source voltage at this point. Now, if you recall, I have applied same inputs at both the terminals. Both the gates are at VICM and VICM. So first step, I'll directly use the brute force way of calculating it. We just saw that I1 plus I2 equals 0. So you get this condition VGS1 plus VGS2 equals 0. And VGS1 happens to be VICM minus, let this node voltage be Vx minus Vx plus VICM minus Vx. So VGS2 is also same. The sum of it is 0. So this implies your Vx should be equal to VICM. So the source voltage here becomes equal to the input voltage itself, which is VICM itself. So that's the difference between the previous circuit. In the previous circuit, if you see, this node voltage came to AC ground. When I say previous circuit, I'm referring to the voltage bias differential pair. This node was at AC ground even in common mode analysis. But now we see in this common mode analysis, this node is no longer at AC ground. This node was at AC ground only for differential inputs. But the moment I apply same inputs at both the gates, this node voltage is no longer at AC ground. And in fact, you can quickly show this using superposition. If I apply VICM here, I'm going to get VICM by 2 due to this. And of course, when I'm applying superposition, I'm assuming this is at AC ground. And finding it out, I get VICM by 2. And because of this, again, we get VICM by 2. So the total voltage will be VICM. So you can apply superposition and solve it the way we did it for the differential input example. So we can do it as well, and we get VICM here. Now that simply means if this source node voltage comes to VICM, then the VGS is 0. Because your VGS gate voltage is exactly equal to source voltage, that means your VGS is 0. If your VGS is 0, then the drain currents both I1 and I2 are 0. If both I1 and I2 are 0, the small signal voltages at the drain terminals is simply the voltage drop across these resistors R. Since the currents are 0, the voltage drops will also be 0. So therefore, I can directly say VO plus and VO minus are both equal to 0. So thus, the common mode gain ACM is exactly equal to 0. So there is no change in the output. Both the outputs VO plus and VO minus are exactly equal to 0. So therefore, this common mode gain for this circuit is 0. Does it matter that the common mode gain, does it matter having a lower common mode gain? Does it help at all? Because in the differential amplifier system, we only care about the differential output. If I still take the output differentially, even though there is 0 common mode here, and in the previous case there was a large common mode input, if I take the output differentially, the ACM DM is going to be 0 for both the circuits. ACM DM is 0 here as well. But the difference here is that ACM is also 0 here. Okay, so does it matter? We will later see that. We will later see most circuits that we build in practice are not purely symmetric. There will be some small mismatches between the transistors and the resistors, because of which ACM DM will not come to 0. Even if you take the output differentially, ACM DM will not be 0. And we will see that for this circuit, when we used a current biasing, your ACM DM will be much smaller in comparison to a voltage biased differential pair. Right now, I'm just putting the thought. Later, when we analyze it, we will see that. When we introduce mismatches and analyze it, you will see that you will understand it with a far better clarity. The other thing is that, does common mode gain matter? It matters because let's say we cascade a set of differential amplifiers. I'm cascading a set of differential amplifiers. When you cascade them, let's say we have some common mode noise at the input which is affecting both the inputs. As I said, it can be from the previous stage's supply. Okay, and so if I have some common mode component that gets amplified once here, and it gets amplified here twice here, and it further gets amplified more and more. And if let's assume at the input your common mode signal is greater than the input signal, then at the output your common mode signal will become so large because it is getting amplified by a large factor. It will become so large that it will even dominate the input signal itself. So that way also we can see that having a smaller ACM helps. Ideally, you don't want even the individual nodes to respond to common mode inputs. So definitely it helps. So to compare these two circuits, which is what we analyzed in the previous lecture and the beginning of this lecture, in this circuit, this is a voltage biased differential pair. We said ACM was exactly equal to ADM. The differential mode gain and common mode gain were same. ACM DM was 0. For this circuit, ACM DM was 0. And for the other circuit here, which is the current biased differential pair or source coupled differential pair, we saw that ACM was 0. Both the nodes were not even changing, even though there was a common mode input at both these inputs. And differential gain was same as this circuit here. Both the circuits had same differential gain. The difference came in the common mode response. The common mode gain was 0 for the second circuit, for the current biased amplifier. ACM DM is same. ACM DM is same for both the circuits. But the huge difference comes in the common mode gain. Now, what we have discussed so far is the different gains, and we took two very standard topologies of differential pairs and analyzed and found the three important gains: common mode, differential, and ACM DM. Now what we are going to do is that we are going to quickly, I'll just introduce you to a simple systematic procedure to calculate these three parameters without having to analyze the full differential pair. If you see, the method in which I was calculating ADM, ACM and ACM DM is that I analyzed both the transistors, I analyzed both the amplifiers which comprised the differential pair, and then calculated all these parameters. So, but then we can see that since both this, in most of the differential pairs, both the arms are purely symmetric, both the arms are identical. So then do we really need to analyze both to calculate all these gains? Or we can generally just analyze one half of the circuit and somehow infer the overall differential gain, common mode gain and ACM DM just from that one half itself. So that idea of developing or trying to find this parameter, the gains from just one half of the circuit, is what we refer to as the half circuit or the half circuit approach of solving these circuits, of solving these differential circuits. So any differential pair can be represented by an equivalent half circuit. And to keep in mind, it's a very important point to keep in mind, is that this half circuit which we are going to introduce now will vary for common mode and differential mode. Okay, so because there is an idea of differential ground, it will vary for common mode and differential mode gains. So first I'm going to tell you how to derive the differential mode gain from a common mode, from a differential amplifier using this half circuit idea, and later we will see how to find the common mode gains. So I'll take the examples of these two circuits and we'll try to find the differential gain of these two circuits by using a common mode a half circuit idea. In the first circuit, this is still a voltage biased differential pair. The approach to draw a half circuit or to derive a half circuit is first to find out an axis or a line around which the circuit is purely symmetric. Now if you recall, we discussed this resistor R can be split as two series resistors of value R by 2 and R by 2. I am just splitting the resistor as two series resistors of value R by 2 and R by 2. And why am I doing that? Because I can then clearly see some kind of an axis of symmetry around which the differential pair will be fully symmetric. So by doing that, I have drawn it this way. See here I have split the voltage source as two identical voltage sources, but remember these two are equipotential surfaces, so I have to replace them with two identical voltage sources. So by doing that, none of the DC operating conditions are disturbed. It's the same circuit, but I've just right now I'll even show the supply voltage. It's the same circuit drawn slightly differently. That's it. So everything is same as it was in the previous circuit. So now here from this circuit, once we have drawn the axis of symmetry, we have already done the analysis of differential pairs. In a purely differential circuit, when you are applying a differential input is purely differential, which means every node in the circuit will be purely differential. So this node is going to be differential, this will also, which means when I say differential, both the nodes will experience opposite voltage swings. If one node is increasing, the other node will decrease by the same amount. So therefore, along this axis of symmetry, the node voltage will come to 0. It will be at 0 AC voltage. Because if this node voltage increases by delta V, this will decrease by delta V. So this node will come to AC ground. So what I need to do is that as soon as I draw this axis of symmetry, all I need to do is to just ground these two nodes. Wherever this axis of symmetry cuts that line, you have to just ground that node. Once you ground that node, you can just see that both the circuits will be identical on either sides. Just take one half of the circuit and do the analysis of that. So this one half is what we call as differential half circuit. So I have shown your differential half circuit here. So this node is anyways at AC ground. So even though there is a voltage source for small signal is concerned, that will anyways be coming to AC ground. So this node is at AC ground. The input is at Vi by 2. I'm applying a Vi by 2 input. And we have a resistance R by 2 in addition to the resistor R here. So at the output, I can model this as a single resistance of value R parallel R by 2, which will simply be R by 3. So the voltage gain for this circuit happens to be minus of Gm into R by 3. So once you draw the differential half circuit, the gain of your differential half circuit will also be the same as the gain of your differential amplifier itself. So that's the advantage of half circuit. Once you draw the half circuit, you don't need to worry about the other half. You just have to find the gain of the half circuit, and the gain of the half circuit will be exactly the same as the gain of the fully differential amplifier as well. The one common question that most students have is that what should be the sign of the gain? What should exactly be, do we know the gain is negative or positive? How do we know that? For that, you'll just have to look at the amplifier configuration itself. So if you look at this amplifier here, it depends on how we take the output and how we apply the input. So if I say this is positive, if I'm saying this is Vi plus and this is Vi minus, that I'm going to apply a negative voltage as compared to the voltage here. So your differential VID is Vi plus minus Vi minus. Then in that case, because it's a common source amplifier, this is going to be positive and this is going to be negative. So if I represent a voltage this way, the voltage across this resistor this way, then V0 will be in phase with Vi, VID or the differential input. It's going to be in phase with the differential input. The thing about differential amplifiers is that the sign is really not that big a concern as we were concerned about in a single-ended amplifier. The reason is that now if let's say we take a single-ended amplifier, let the amplifier's gain be minus A. The output of this amplifier will be minus A times Vi. And it's very important for me to specify the gain here, the polarity of the gain as well, because the output is just, it's a single terminal output, you are going to get minus A times Vi. If I want to get positive gain out of it, I have to insert another amplifier with a gain of minus 1. Then at the output of this amplifier, the gain becomes positive. The gain of this composite amplifier is positive. The thing about a differential amplifier on the other hand is that if I say that this is positive and this terminal, the output terminal is VO plus, it's in phase with the input. And if I want to invert this, if I want to get a negative gain out of it, all I need to do is just flip the terminals. I just have to flip the terminals. So then the gain becomes negative. So that's why the polarity really doesn't matter here. So you can get positive or negative gain using a differential pair by just flipping the terminals. So if I take this way, if I get positive gain, I can always flip the terminals and take the output and you will get negative gain. So that's why gain is really not important. Just take the sign, the magnitude of this from the half circuit. Once you draw the half circuit, measure the gain and take its magnitude. That will be your voltage gain of your differential amplifier itself. So now we'll try to draw the other circuit. We'll take the other circuit and try to find the differential gain by using this half circuit. So again, I'll have to split the circuit in such a way that there is an axis of symmetry around which the circuit is a perfect mirror image of each other. So here I'm taking this current I and splitting it as two currents, I by 2 and I by 2. Because I have to not violate Kirchhoff's current law. At DC the both should look the same. Okay, so you have a current I by 2 flowing here, I by 2 flowing here. So Kirchhoff's current law is not violated. So it's same as this circuit. So draw a line of symmetry. Now if you see the circuit is purely symmetric on either directions, then this node, wherever it's cutting at the supply, and this node will be at AC ground. And forget about the other half, draw only one half, you have your differential half circuit. So the current source is shorted out because this node comes to AC ground. So this node is at AC ground here, and the circuit reduces to something like this. And the differential gain for this is minus GMR. As I said, sign doesn't matter, it will just be GM times R. So the differential gain is simply the gain of the half circuit, the differential half circuit. Now again, I'll take one more circuit and try to find the differential gain using the half circuit concept. So if I take this circuit, here I'm just making one small assumption. So first let me just ignore the resistor and try to draw the half circuit. So first, the same way, whenever you have a resistance in between the positive and negative terminals, split it into two equal halves, so R by 2 and R by 2. And then now you see I can draw a line of symmetry here. Around this axis of symmetry, the circuit looks purely symmetric on either directions. I've split the current as I by 2 and I by 2 here. So this node here will come to AC ground. Both these nodes, and in fact this node will also get AC ground. Now why does it come to AC ground? So this is something I have already discussed in the previous lectures. It comes purely because the system is a differential system. These two nodes will be differential. If these two nodes are differential, the node at the center will be at AC ground. So same way, we discussed why this node also comes at AC ground for a differential input, because it's a differential ground. Few more in the first example when we began this lecture, I argued why it comes to the differential ground. So right now, when we are talking about a methodical procedure, we don't have to worry about that. You just have to draw the axis of symmetry, and this node will come to AC ground. So this is AC ground only for differential inputs. So then the differential half circuit just reduces to something like this. Source is at ground. At drain we have, I'm just going to ignore the current source in AC analysis. So we have resistance R by 2, and the DC gain or the differential gain is simply GM times R by 2. There is a minus sign, but we said we don't worry about the sign. The gain is simply GM times R by 2. Now we will try to similarly develop a same idea for finding the half circuits for common mode inputs. Now the method of finding common mode, I'm going to apply same inputs at both the terminals, and then short circuit the output, or it's equivalent to short circuiting it because both the inputs are going to change by the same way. I'm just going to find out the average value of the outputs. That should be equal to VOCM by VICM, which will give me my common mode gain. Again, I'll take the same circuits which I took for analyzing the differential half circuits. I mean trying to find the differential gain using differential half circuits. So the first approach, to draw a common mode half circuit is same. So I have taken these two circuits here. I'll first consider this one. The first approach is to just draw the half circuit. So take the circuit, split it into two. So there is VDD here. I'm splitting into two so that you can draw an axis of symmetry around which the circuit will look purely symmetric. Now the difference in case of a common mode half circuit, what you need to do is that you need to you need to cut your circuit into two at the node where the line of symmetry intersects the lines here. Any nodes in the differential amplifier, just open circuit them. In case of a differential half circuit, you are short circuiting them. In case of a common mode half circuit, we are open circuiting them. Why are we open circuiting them in common mode half circuit? The reason is pretty simple, because if both the nodes change in the same way, this node is going to change by delta V, this will also change by delta V. So even though they are short here, there is no current flowing between these two terminals. So there is no current flowing here between these two. Therefore, it's like an open circuit. I just open circuited it. So since no current is flowing between these two terminals from here to here, we said we can just open circuit that node. Once you open circuit it, just take one half of it and draw AC equivalent and find the gain. That's your common mode half circuit. So I've shown here, this is your common mode half circuit. Now you have a resistance R by 2 here, but since this node is open circuit, there is no current flowing through that. The voltage drop across R by 2 will be 0. So therefore, it will act like a short circuit. So I can just remove this and simply represent this circuit this way. So now draw the small signal model. This voltage source will be at AC ground and VDD is at AC ground. So you get this. Once you get this, the common mode gain can be found by finding the gain of the half circuit, which happens to be minus of GMR. So this is a voltage biased differential amplifier, and we are not surprised that we get a very high common mode gain, which was the same as what we derived in the previous lecture. So we found the common mode gain using the common mode half circuit approach, and we intuitively said, okay, why does it make sense to open circuit this node? In case of a common mode half circuit, there are two approaches by which you can draw the common mode half circuit. The first approach is what I discussed now, open circuit and pick one half of that and do the analysis on that half. The other approach is to recognize that both these inputs change by the same manner. If both these inputs are going to change, whenever you draw the axis of symmetry, every node on either sides of the axis of symmetry will see same variations. So I might as well short circuit those nodes because there is no current flowing in this R by 2 and R by 2. I might as well short circuit the two nodes. If I short circuit them, then what happens is the width of the MOSFETs become doubled, and the resistors, because you see now we have two resistors in parallel, so we get R by 2, R resistors become half. Okay, so but since it's a voltage source in parallel with voltage source, you get the same voltage here. So the equivalent circuit can be drawn this way as well. You can just reduce it to a single amplifier by just shorting every node. Or otherwise, what I normally refer to is fold the circuit and overlap on top of each other. So around the axis of symmetry, you just have to take this half, fold the circuit and overlay on top of this. When I overlay on top of this, the VCM, the gate here connects to the gate, and this resistor, anyways, the source is already at, probably I should show it this way. So this node the supply is already shorted here. So you have to just take this half and fold it around the axis of symmetry and overlay on top of this. you get the same circuit. When you do this folding and overlaying, you get the same circuit here. So the width becomes 2W, resistance becomes R by 2. In fact, I haven't shown what happens to this resistor, so which is, you have R by 2 here. When you fold it around this node, you get another R by 2 coming in parallel with this. So finally it becomes R by 4. So this becomes R by 4. But since this node is open here, even though I am folding it, this node is open here. There is no current flowing through this node. So the voltage drop across this resistance is 0. So I can simply ignore it and short it out. So from this, once you draw the half circuit, perform a small signal analysis and compute the common mode gain. So this will be at AC ground. So the gain for this circuit, so there is one important point here is that, so this is a voltage biased amplifier. In a voltage biased amplifier, if you see, the VGS is fixed, source is at a fixed voltage, gate is at a fixed common mode voltage. So drain current is given by beta n by 2, beta n is mu n C ox W by L, times VCM minus VS minus VT the whole square. Since this term is fixed, if I am doubling the width, if I am doubling what I have shown here, doubling the width, beta n is doubling, so which means your drain current will also double. So drain current is doubling, beta n is width is doubling, so then GM will also become 2GM. So that's what happens when you perform the common mode analysis, common mode half circuit analysis, and when you do this folding, or you can or shorting each node, whatever you want to call it, but when you do this, the GMs of the transistors will become 2GM, resistors will become R by 2. So the voltage gain of this is minus 2GM times R by 2, so you get a gain of minus of GM times R, which is same. So whether you follow the first approach, the first method, where we open circuit the nodes and just analyze one half of the circuit, or the second approach where we overlay, we fold the circuit around one node. Literally you can imagine as though you are folding this plane onto this circuit here, and then after folding it, you have the circuit reduced to a single circuit with twice GM and resistance as R by 2. Then perform small signal analysis and compute the gain. The gain you get from both the approaches will be exactly the same. It shouldn't differ, and you can choose whichever approach you find convenient. So that's it about common mode half circuit. So we'll take probably one more example. So how to find common mode gain using common mode half circuit. So in this circuit again, I need to first draw a half circuit. So for that, I'll have to short this. I'll have to represent the current as split it into two halves. So I by 2 and I by 2 here. So you get I by 2 and I by 2 here. So the axis of symmetry is here. Open circuit the node around that axis of symmetry, and you have the common mode half circuit. So you just have to consider one circuit here, one half of it, you get the common mode half circuit. Now from this, then apply AC analysis. So open circuit the current source and calculate the gain. So when I open circuit this current source, the small signal current flowing through this is 0. If the small signal current is 0, GM VGS is 0. If GM VGS is 0, VGS is 0, which implies the gate voltage is equal to the source voltage. So this node voltage will also come to VICM. Since the small signal current I is 0, the voltage drop, the small signal voltage drop across the resistor will also be 0. So therefore, we will get the output common mode voltage will be 0, the common mode gain will also be 0. So now if you recall a few moments back when we were discussing the differential half circuit of a current biased amplifier, it is very different. The differential half circuit is very different from a common mode half circuit. Whereas if you see a voltage biased amplifier, the differential mode and common mode half circuits were same. But when you go for current biasing, that's where the difference comes. The common mode half circuit is different, and therefore you get a very different common mode gain as well. So we got a 0 common mode gain for this circuit. Similarly, you can apply the second procedure as well. So that is the second method. You can take draw an axis of symmetry and fold this arm on top of this. So this node will overlay with this node. This is already shorted. Okay. So and anyways the inputs will both be overlaying on top of each other. When that happens, the device width is 2W. Now you see the current flowing through that is I, because I'm overlaying it. This current source gets added to this current source, so you get a current of value I. So current is doubled, width is doubled, so therefore your GM will become 2GM. So that's what I've shown here, the AC equivalent. So I have not shown the current here. So you'll have a current of value 2I, width being 2W and resistance being R by 2. You should keep in mind that the DC conditions should remain the same when you're doing this transformation. So here if you see the DC voltage here at this node is VDD minus 2I times R by 2, which is VDD minus IR. Okay, so the VDD minus IR is the voltage across this. Now similarly, I can actually show that, I'm sorry, this is not 2I, this is I here. So this is I, so I by 2 plus I by 2 is I. So we get VDD minus IR by 2. So this is I into R by 2. So we get VDD minus IR by 2 as the DC voltage here. Before overlaying in the differential circuit, the DC voltage here is also VDD minus IR by 2. So that is preserved. Then after that, once you overlay on top of each other, then all you have to do is find out the small signal AC gain and open circuit the current source and short circuit the DC voltage sources, you get it. So since the source is open, this node will also come to VI and the output voltage will go to 0. The drain current will be 0, so it goes to 0. So I can say ACM will be 0. And if I'll just add one point here, how to draw the equivalent circuit in the presence of when we have a resistance ROC in parallel with the current source. So again, I have already analyzed this circuit as well. Now what I'm going to do is that I'm going to assume that this resistance, this current source has a finite resistance R, and we will try to find the differential and common mode gains for this circuit using the same approach. In fact, we already found the differential gain. So first I'll assume this current source is an ideal current source, and then we will see how to find the differential and common mode gains in the presence of a finite current source output resistance. So here again I'm going to split this resistor into two, R by 2 and R by 2. The current sources are also split as 2. So this is your axis of symmetry. For a differential circuit, we already analyzed this. In a differential circuit, the gain turned out to be, so this node will come to AC ground, this node will also come to AC ground, this node will also come to AC ground. So the circuit will simply reduce to something like this. So you will have R by 2 in parallel with R, you will get R by 3. So the gain is GM R by 3, the differential gain. But what about the common mode gain? So if we were to find the common mode gain for the circuit, what we need to do is that first we'll open circuit this node, and draw the half circuit. So I'll open here and this will become VDD and VDD. So from this half circuit, we can directly calculate the common mode gain. So from this half circuit, the common mode gain, we analyzed it just a few moments ago. This resistance R by 2 really doesn't matter because there is no current flowing through that. So I'll short it out. We can directly say that the VGS here will come to 0. So therefore, the common mode gain will be 0 for this. So VGS is 0, so the drain current flowing through this will be 0. So the small signal voltage drop across all will be 0. So the common mode gain will be 0 for this. The next lecture, I'll introduce a resistor R of finite value and show what impact does this resistance have on differential mode and common mode half circuits and gains as well.